case, if you look at this DS diagram, as for this schematic diagram, we are going to look at this DS diagram, convert to schematic diagram. So you want this to be one shaft or two shaft? Guys, you want me to sketch a schematic diagram, two shaft or one shaft? If two shaft, meaning that the high pressure turbine will run the compressor, while the low pressure turbine will run the electrical generator. If one shaft, I will attach all the components involved, which is the main component involved in one shaft is the compressor, high pressure turbine, and low pressure turbine. So you want me to sketch which one? Separate shaft or the same shaft?
First, same shaft.
Same shaft. Or you want me to sketch both?
Yes.
Okay, all right. Okay, thank you. Okay, I will show you the first one, which is one shaft. Okay, one shaft first, right? Okay, so we have our compressor, only one compressor in this case involved. Okay, we can see that the only compression process is from 1 to 2. Okay, after that we have our turbine, which is the high pressure turbine. This is our compressor. And then we have another shaft, extension of the shaft going to the second turbine, which is referring as turbine low pressure, and an extension of the shaft to run an electrical generator. Okay, so we know that before this is a reheat process. Okay, reheat process. Therefore, we have a combustion chamber before entering the high pressure turbine, and then we have the reheat process, second combustion chamber, going into the second turbine, low pressure, and then from here we are going to link the flow at that point, and then we know that we have a heat exchanger or regenerator, and this the purpose of the regenerator is to heat up the air after compression process. So this is the air after compression process. So we are going to heat it up. Who heat this air? The air is heated by the exhaust gas from the low pressure turbine. Okay, so this is our heat exchanger. This is our combustion chamber number 1. This is combustion chamber number 2. Of course, we know that the air will be sucked in from the ambient to the first compressor. And then we are going to have the compression process. And then after that, reheat process. After that, combustion process in CC1. And then we have expansion process, high pressure. Then going into CC2 for reheat. And then after reheat, going into the low pressure turbine and exhaust gas. Going into the heat exchanger. This is our heat exchanger. And this will be exhaust from the plant itself. Right? So let us put the numbering 1, 2, 3, 4, 5, 6, 7, and 8. How come 7 and 8? Oh, sorry. Sorry guys, I have to follow this type of numbering. Okay, it's too prime. Sorry for that. Erase all the numbering. Okay, again, this is 1, 1 to 2, 2 to 2 prime. Okay, and then we have 3. After 3, we have 4. Sorry, 4. This is 4, first turbine. And then we hit 5. And then we have 6 right here. And then we have another point, which is point 7. Where is point 7? Oh, sorry, again, not point 7, but in this case, it's 6 prime. 6 prime. Okay, 6 prime. So this is our 6 prime. Right? So this is the schematic diagram if we use single shaft. And in this case, if we try to look at the W net, this should be equal to the W for the first turbine, V4, plus the W for the second turbine, low pressure, which is 656, minus W compressor, W12. So as far as W net is concerned, if this type of arrangement, then we need to get the W net from this equation. Okay? And then the second arrangement, the second schematic diagram, whereby we have 2 shafts. First shaft, of course, the high pressure turbine, we run the compressor. This is our compressor. This is our turbine, high pressure. To that, we have the low pressure turbine. And the low pressure turbine is running the electrical generator as our output. So this is turbine, low pressure. Again, of course, before the first turbine, we are going to have a combustion chamber. And due to reheat process 4 to 5, we are going to have second combustion chamber. And then we have the reheat process, regen 2 to 2 prime. Then it will be used to heat up the air after compression process. Then this will go to the first turbine. This is for the reheat process. Expansion, low pressure turbine. And we have right here is our regenerator using the heat exhaust from the second turbine to be used as to heat up the air after compression process. Okay, so this is our CC1. This is our heat exchanger. This is our CC2. Okay, then flow in surrounding air 1, compressed air 2, regen 2 prime, then exiting CC1 into high temperature, high pressure turbine S3, exhaust before entering CC2 is 4, 3, 4, and then the reheat process 5, expansion after low pressure turbine is 6, and then exhausting right here is 6 prime. Okay, so this type of arrangement, then we could write that our compressor work W12 is equal to the work produced by our high pressure turbine. Okay, so this is 3 4. And then we are going to get the W net equal to the expansion from 5 to 6. Okay, so what we have? We can also determine from this type of two-shaft schematic diagram or arrangement, we can also get the W net from the first law of thermodynamics, whereby the W net is equal to W34 plus W56 minus W12. You see, we have the same equation here. But what we can do right here is we know that the W12 is equal to W34. This could be cancelled off. So what is left is still W56. Okay? So that is our W net. Any question? Right. So in this case, we have extra point. Okay, extra point or extra state. All the state of 1, 2s, 2, and then state 3, 4s, 4, 5, 6, 6s. We are going to do the same thing as what we have learned before. We have looked before. Now we have to determine what is 2 prime and 6 prime. Why do we have to determine 2 prime? Because we are going to look at the new Q in, whereby the Q in is from 2 prime to 3 plus 4 to 5. Okay, Q2 prime to 3 is 1. Okay, so we are going to have the Q in. I haven't mentioned that before. Okay. So now we have the Q in. So how to calculate the Q in, or to calculate the Q from 2 prime to 3? This is by using the formula of CP G T3 minus T2 prime. Therefore, we need to get what is 2 prime. So how to get the 2 prime? The 2 prime we are getting from this thermal ratio definition, which is the increment of air temperature at the heat exchanger or regenerator, which is from 2 prime to 2, divided by the maximum possible temperature difference that we have from the plant, which in this case, the maximum temperature difference we could have is from 6 to 2. That is the available type of Q, the available of energy from the waste heat. Because if we want to heat up the air, we are going to heat up from point 2. Okay? So the 2 prime and 6 prime, usually I would suggest to students to put at same level. Okay, about the same level. I will show you why it's about the same level. Okay? So this equation is in order for us to get the T2 prime. And you see that to get the T2 prime, we need the T6. Okay, we need the T6. Where is T6? T6 is the temperature after the second expansion here. Meaning that when you define all the temperature of this cycle or this plant, we are going to determine 1 to S2. The 2 prime, we have to KIV first because we need T6. Then we go for the 3, 4, 4S, 4, 5, 6, 6S. Once we have determined the 6, then only we can go back to the equation of the thermal ratio in order to get T2 prime. Right? How about T6? Do we need the T6? guys, as far as the work net is concerned, okay, as far as the work net is concerned, as far as the thermal efficiency is concerned, as far as the thermal ratio, the work ratio is concerned, all these three parameters, do we need 6 prime? What do you think? The temperature of 6 prime. When determining the W net, again, when determining the thermal ratio, when determining the work ratio, right? In these three parameters, these three properties, do we need the T6 prime? What do you think? What is W net? This work plus this work minus this work. Okay, that is W net. What is thermal ratio? What is the thermal efficiency? W net divided by this Q in plus this Q in. Work ratio, W net divided by this work plus this work. Do you think we need the T6 prime?
I think no need.
No. Right? As far as that three parameters is concerned, that is the W net, thermal efficiency, and work ratio, we do not need the T6 prime. So when do we have to find the T6 prime? We have to find the T6 prime when the question asks for it. So please take note. Okay, we only need the T6 prime when the question asks for it. So now how to get the T6 prime? If the question asks what is the temperature of exhaust gas from the plant, so the exhaust gas from the plant is T6. You see right here, T6 prime. This is the exhaust gas from the plant, T6 prime. This is the exhaust gas from the plant, T6 prime. So what we do, we look at this heat exchanger. Okay, we look at this energy balance inside this heat exchanger. So what we have right here, we are going to have the amount of Q rejected from 6 to 6 prime is equal to the amount of heat received by the air from 2 to 2 prime. And in this case, we are going to use this Q dot and Q dot. Meaning that if this is Q dot, so this is M dot CPG T6 minus T6 prime. And this is equal to M dot CPA T2 prime minus T2. Okay? So this is where we have T2 prime minus T2. And we know that the mass of fuel is negligible. Therefore, this could be cancelled off. The M dot is equal to M dot A. And if we assume that this is equal, okay, the M dot CPG is equal to M dot CPA. This is the assumption made. When this assumption is made, then what we have right here is the T6 minus T6 prime is equal to T2 prime minus T2. You see there? So this is thermal ratio equal to T2 prime minus T2 equal to T6 minus T6 prime. Divided by same thing, T6. Okay, T6 minus T2. Can you see this? This part, which is equal to this part. The temperature increment equal to the temperature difference between 6 and 6 prime. The temperature increment of the air is equal to the temperature decrement of the exhaust gas in the heat exchanger. So this is the method used in order to get T6. So please take note what I have mentioned before. The T6 prime, initially we don't need in determining the three main parameters. We only need the T6 prime if the question asks for it. Okay? So that's how we look into this case. Any question? All right. If no question, I want to continue with the question 9.2. I think the question 9.2 we have did, right? Remember the question 9.2? Let's recap back question 9.2. Let me print screen. Okay, this is question 9.2. Okay. Still remember, I think we have, can you please tell me, I think we have solved everything, right? For this 9.2. Can anyone verify that? Guys? Anyone verify that?
I think not yet, Doctor.
Huh? Is it?
Yeah. Oh, and Doctor, the WebEx chat meeting still is not available.
I have unchecked everything or want to check or uncheck?
Need to check, Doctor.
Participant assigned privileges. Uncheck. Oh, check again, Tiba.
Must check everything, Doctor.
Check all.
Yeah.
Okay.
All right, now can, Doctor. Thank you.
Betul ke Tiba? Kita tak buat lagi ni?
Belum sir. Kita tak pernah buat ratio 4:1.
Tak ada Alright, okay. If not, we are going to do it. Right. Okay. Let us do I thought I had mentioned that the one that we did is the propeller This is marine gas turbine. Oh yeah, betul lah propeller. I thought I have changed this propeller to our electrical generator. Okay, tak apalah. We maintain the same question, the original question. Okay, in a marine gas turbine unit, the high pressure stage turbine drive the compressor and low pressure turbine drive the propeller through a suitable gearing. The overall pressure ratio is 4/2. The mass flow rate is 60 kg per second. The maximum temperature is 650 and the air intake condition is 1.01 bar and 25 degrees C. The isentropic efficiencies of the compressor, high pressure turbine and low pressure turbine are 0.8, 0.85 and 8.83 and 0.85 respectively. And the mechanical efficiency of both shafts is 98%. Neglecting kinetic energy changes and the pressure loss in the combustion chamber, calculate. Okay, confirm tak buat lagi
No, doctor. Belum, Ustaz.
Okay, so what is the first thing that we need to do? What guys? Apa dia the first thing that we have to do?
Schematic diagram.
Schematic diagram. Okay, we need to ask ourselves, how many shafts?
2.
2 shafts. Why 2 shafts?
Because the high pressure drives the compressor.
Okay, so the high pressure will drive the compressor. So we sketch the high pressure which drive the compressor. Compressor, turbine, high pressure. First shaft. Next shaft. Which one? The low pressure drive the propeller. Okay, drive the propeller. Right. We have overall pressure ratio 401, mass flow rate 60, maximum temperature. So maximum temperature usually from the first combustion chamber before entering the first turbine. So this is 650. 650 degrees C. Intake condition should be our condition of suction part of the compressor. So this is 1.01 bar and the temperature is 25 degrees C. And then we have all the efficiencies, isentropic efficiencies, and we have mechanical efficiency. So right here, we have mechanical efficiency for the first shaft and also for the high pressure shaft, mechanical efficiency, 0.98. Okay, so to complete our flow, nothing mentioned about the regen, nothing mentioned about the reheat. Okay, nothing mentioned about the regen and nothing mentioned about the reheat. So what is coming out from here, we are going to throw it to the surrounding. Right? So let us put the arrow, arrow, arrow. Okay, let us put the numbering. 1, 2, 3, 4, and 5. Okay. Now we look at the definition of mechanical efficiency. So we have mechanical efficiency on the first shaft. What is efficiency? Efficiency is defined as the desired output divided by the required input. Okay, so from this shaft, where is our desired output?
Compressor.
Compressor. So right here is W12. Required input from the turbine, 3, 4. Next, second shaft. What is our mechanical efficiency? Desired output. Which one is our desired output? The popular work, correct? This is the gearing system, the popular work. And this work is assuming STW net. Divided by the required input is from the work produced by the low pressure turbine. So W 4, 5. So what do we have from this schematic diagram of the mechanical efficiency? So what we have right here, okay, so we are going to put down the W12 equal to mechanical efficiency multiplied by the work for the high pressure turbine. Is what we have. From the second shaft, what do we have? The W net is equal to mechanical efficiency multiplied by the W 4, 5. Okay? And to complete the data given, so overall pressure ratio. So what is that? 4/5. Maximum, look at the compressor side. It should be P2/P1. This is the maximum for compressor, minimum for the compressor. When we look at the turbine side, this is the maximum for the turbine. And this is the minimum for the turbine. This is equal to 4/1. And if we look in terms of the pressure ratio at the turbine side, the relationship that we could get in terms of pressure ratio, we are going to have P3/P5, which is the overall pressure ratio, is equal to the individual pressure ratio P3/P4 multiplied by P4/P5. So this is the relationship in terms of pressure ratio for the turbine side. Okay, for the turbine side. This pressure ratio multiplied by this pressure ratio then is equal to the overall pressure ratio. Okay, and then apart from that, we have our 60 kilogram per second, which is our m dot. And we have the individual isentropic efficiency. Compressor, high pressure turbine, and low pressure turbine. So we have our separate value of efficiency. Isentropic efficiency for compressor, which is equal to 0.8. Isentropic efficiency for the turbine, So this is for the high pressure turbine. (0.83). And then lastly is the isentropic efficiency for the low pressure turbine, which is equal to 0.85. Okay, and also please don't forget the mechanical efficiency is given as 0.98. Okay. So what are we going to do next? Is to get all the temperatures. Okay, let us do together. What is T2? Are we going to get T2 or, oh, sorry, before that, we need to sketch the TS diagram. Let us sketch the TS diagram first before getting all the temperatures. How many pressure? 3 pressure. Intermediate pressure. Compression process. Expansion process. Without reheating. Okay. Heat in, Q in, combustion chamber. 2, 1, 2S, 2, 3, 4S, 4, 5S, 5. Okay? So now let us get all the temperature. So which temperature that we are going to have? The T1 is given 25 plus 273. Next, 2S or 2? Guys, next 2S or 2?
2S.
2S. So T2S equal to T1 P2 over P1 gamma A minus 1 over gamma A. Okay, please remember for this question, the gamma, okay, please take note, right? Please take note. The CP for air 1.005, gamma for air 1.4, CP for combustion gases 1.15, and the gamma is 1.33. So the CPA 1.005 kilojoule over kilogram. Gamma A 1.4. Okay, and the CPG 1.15, and the gamma G is given as 1.333. Okay, using that CPA, gamma A, get your T to S. Okay, how much?
442.8.
442.8 Kelvin. Someone, can you please verify that?
Correct, Doctor.
Okay, thank you. Based on the isentropic efficiency of the compressor, shorter line divided by the longer line, to get your T2. Okay, anyone? T2?
Four 479.
Tak dengar.
479.
Point?
0.04.
Someone verify?
Same value, Doctor.
Thank you. T3. Given. Okay, how are we going to get next one? Are we going to get T4 or T4S?
4S.
How to get T4S?
T4S equals to T3, P3, P4, P3, gamma G minus 1 over gamma G.
How do we get the P3 over P4?
Overall ratio.
How to get? Do you know the P4 over P5? This one. We need the P4 over P3, correct? We know the P3 over P5. We want to get P3 over P4. Do we know P4 over P5? No, we don't know. Alright? So in this case, this one we keep IV first. Because we don't know what is this. The problem is we don't know what is this. So what's next? With this, we have this equation. This one. Okay, W12 equal to mechanical efficiency W34. So we can IV that first. Then we go for the next equation, which is W12 is equal to mechanical efficiency W34. Okay. Then from here, what is W12? W12 is CPA T2 minus T1 equal to mechanical efficiency CPG T3 minus T4. And if we analyze each parameter, CPA okay, T2 okay, T1 okay, mechanical efficiency okay, CPG okay, T3 okay. So what are we going to get? T4. Not this, okay? So we are going to have the T4 first. You get your T4? Okay, new one.
Seven six 761.56.
761.6.
56.
Okay, someone verify for that?
Same.
All right. And then we are going to use the isentropic efficiency for turbine high pressure, which is equal to T3 minus T4 divided by T3 minus T4S. Okay, we have this, T4, we have it. Then from here, we are going to solve for T4S. Okay, get your T4S.
Seven to 8.54.
7 to 8.
0.54.
Okay, someone verify that?
Same.
All right. Next, what are we going to have? T4 complete. Then we go for T5S. Okay, how to get T5S? Which formula that we're going to use? T5S equal to T4. Okay, which T4 is that? Right, we are going to look 4 to 5S. Okay, 4 to 5S. So is T5 equal to T4 P5 over P4. Gamma G minus 1 divided by gamma G. So we need the P5 over P4. So we are going to use this relationship of the pressure ratio. Right? So from here, from the pressure ratio, which is the P3 over P5 equal to P3 over P4 multiplied by P5 over P4 over P5. So in order to get the P5 over P4, then we need this P3 over P4. This is already given. Then from this equation that we KIV, right, the KIV, we could get what is P3 over P4. So from here, we are going to get the P4 over P3, okay, P4 over P3 is equal to T4S divided by T3. Okay, this bring to the left. Then what we have right here is gamma G divided by gamma G minus 1. Okay, get your P4 over P3.
Zero point 3878.
Okay. Can someone verify that? So we need P5 over P4. So what is P5 over P4? P5 over P4 in this case is equal to P5 over P4, P3 over P3 over P4 multiplied by P5 over P3. Correct? We want to get what is P5 over P4, so this one bring to the left. P5 over P4 equal to P3 over P4, right? We bring to the right, P5 over P3. Okay. We have here P3 over P4, then P4 over P3 is this, then this is 1 over 0.3878.
Doctor, for the power tadi, P4 over P3, memang dia,
Power?
yeah, tadi for the 0.3878,
Pressure ratio.
pressure ratio, the power tu like gamma, betul ke the power, the gamma G over gamma G minus 1? Isn't it terbalik? Like,
Kejap. Betul lah. I got from this equation.
no, the power.
From this equation. You see, this is P4 over P3. Kalau P4 over P3, this is the power. So now I'm putting this power to the left.
Oh, okay, alright. Sorry.
Okay. So P3 over P4 is 1 over 0.3878 multiply P5 over P4 is 1 over 4. What is that?
0.6447.
0.6447. All right. So get your T5S. From this equation.
Six, eight, two.
682.5.
0.5.
Thank you. Someone verify that? Isentropic efficiency for turbine low pressure is equal to T4 minus T5 divided by T4 minus T5S. We have this, we have this, and this, and we get T5. Okay, how much is that? T5?
694.4.
694.4. Thank you. Okay, so right now we have got all the temperature, right? So what is the first question? The first question is asking for the P4 over P5. So the first question. The first question is asking for, let me see, the pressure between turbine stages. The pressure between the turbine stages, meaning that P4. Okay, we have to get the P4. So what is P4? We have P4 over P5, right? So number one, P4 over P5. P4 over P5. Oh, sorry, we have P5 over P4. P5 over P4 is equal to 0.6947. Therefore, P4 is equal to, the P5 is the ambient pressure. Okay, the lowest pressure, P5. In the question given the P5 as 1.01. Correct? Yeah, 1.01 bar. Get your P5, P4, sorry. The pressure in between the turbine stages, which is P4, P5, P4, sorry. So 1.01 times this. Sorry, it's divided. Divide kan? Ke? P4 is equal to P5 divided by
Divide,
0.
sir.
Divide. How much is that? .05 divided by this. Berapa? 1 point? Namanya?
1.5.
2 decimal point. 2 decimal point, guys.
1.45.
1.45. Betul kan?
1.511.
1.5? 1.
1.5 11.
1. Okay, 1 bar. So what is the answer in the question? The answer is 1.57. I don't know where does this extra comes from. Okay, tak apa. It's okay. Number 2, cycle efficiency. So number 2, cycle efficiency. Our Q in, our Q23. And the W net right here is equal to W, sorry. We have as mechanical efficiency multiplied by W 1.3445. Okay, this is our equation just now. This one. W net is equal to mechanical efficiency multiplied by W 45. So this should be our mechanical efficiency 0.98 multiplied by our 45 is CPG T4 minus T5. Get our W net. And then Q23 is equal to CPG T3 minus T2. Okay, get the W net and get the Q23. Okay, W net. Okay guys, W net.
Seven 5.08.
Q23.
Five 510.6.
510.
Yes.
Point.
0.6.
Therefore, our thermal efficiency W net divided by Q23. Alright.
Zero point 0.1%.
Percentage.
Percentage. 41.
14.7.
40.
14.7.
14.7. Okay. Then the next question is to get the shaft power. Okay, the shaft power 3. The power of the shaft is equal to m dot multiplied by W net. And maybe as extra, you can also try to find out what is your work ratio. W net divided by W gross equal to W net divided by W. W gross is W34 plus W45. Okay, what is the power?
Four 4504.8.
4504. 4504.8 unit
Kilowatt.
kilowatt. Work ratio so you need to calculate what is your W34 and you need to calculate what is your W45. right? So try to get the work ratio. Now we go to the next question, is the 9.3. 9.3 question. This 9.3 is the continuation of 9.2. So this is 9.3. Oh, tak ada. Okay. Screen. For the unit of problem 9.2, calculate the cycle efficiency obtainable when a heat exchanger is fitted. Assume the thermal ratio of 0.75. Okay, now we have the usage of a heat exchanger. Okay, heat exchanger. So at your schematic diagram, you add up a heat exchanger before your combustion chamber or after your compressor. I'm going to sketch the TS diagram. So let me sketch the TS diagram. All right. Suspension. This compression. Okay, let's say this is the process. Okay, this increment, let's say this is 1 to S 2. Let us take this as a 2 prime. This is 3. This is 4S. This is 5. This is a 5S. This is 5. Sorry. 6. 4, 5, 6. 6S. This is 6. Then we have another point, which is as the 6 prime. See how I sketch the beginning of the heat exchanger process for the exhaust gas. Is from 6 to 6 prime. Okay. So we want to get what is the cycle efficiency. This is our TS diagram. then the cycle efficiency in this case is equal to the W net divided by the Q in. And in this case, the Q in is from 2' to 3. As for the W net, this is same as 9.2. Okay, and this Q 2'3 is equal to CPG T3 minus T2 prime. And if we look carefully, where is our A and where is our B? From this point to this point and to this point. So this should be our B and this should be our A. Okay, so from the thermal ratio, which is equal to A over B, what is A? A is a T2 prime minus T2 divided by B is T6 minus T2. And in this question, given the thermal ratio is 0.75. Okay, so this is given. This we have obtained before this. T6 we have obtained as from 9.2. Then we are solved for the T2 prime. So try to get the T2 prime. Yes, T2 prime.
640.6.
640.6. Anyone can verify that?
Same value.
Same.
Okay, thank you. So once you have your T2 prime, okay, then you will get your Q2 prime 3. Get your Q2 prime 3. and also get your thermal efficiency. Okay. Q23.
324.88.
Thermal efficiency.
23.1%.
Okay. Before this, how much we get the thermal efficiency? We got the thermal efficiency before this is 14.7. Okay, 92, 14.7. Now, with the usage of a heat exchanger, we are getting 23.1. You see, we can increase the thermal efficiency by using the heat exchanger or regenerator. Hey guys, any question? Any
No
question?
questions from me, Doctor.
Okay. No question. I'm going to look at one past year's test 2 question, which is on the gas turbine plant. Okay. In this question, given the schematic diagram of the plant, so please take note, this is the question from test 2. Semester 1. So what I want to do, we are going to sketch the schematic, the TS diagram. This is the schematic diagram, okay? This is the schematic diagram. Now we are going to sketch the TS diagram. And before that, before we sketch the TS diagram, several questions that we have to ask ourselves, right? What do you think that the question should be asked before we can sketch the TS diagram? Anyone have idea? What type of question that we have to ask ourselves first before we can sketch the TS diagram with this type of arrangement?
Mechanical efficiency, sir.
Okay, mechanical efficiency.
Component involved.
Okay.
Component involved, sir. Something like
These are the component involved.
Same shaft, sir.
Yeah, this is same shaft.
Pressure ratio.
This is the same shaft. Yes, we need to know the pressure ratio of what?
overall, sir.
Overall, okay, overall, lagi?
Compressor and turbine.
Compressor dengan turbine. Lagi?
The M dot, sir. M
Yeah.
dot P1, T1.
Pardon?
Intercooling.
M dot
Okay.
P1.
P1, T1. Intercooling. Okay, intercooling, siapa cakap tadi intercooling? What do we need in terms of the intercooler? Yeah. What do we need?
Complete intercooler, sir.
We need to know whether the intercooler is complete or not. Okay. So right now, what I'm going to do is to give you the information of this schematic diagram. This is the only information given. Okay, consider an ideal gas turbine plant. What is the meaning of ideal gas turbine plant? Anyone? What is the meaning of ideal gas turbine plant? Yes? Anyone? Ideal. Anyone? Ideal.
Isentropy 1.
1. For all the compressors and turbines. Okay? Consider an ideal gas turbine plant. Ideal meaning isentropic efficiency is equal to 1. As shown in figure Q2, this is the figure. The plant comprises of 2 stages of compression and 2 stages of expansion. Okay, first stage of expansion, 2 stages of compression and 2 stages of expansion. This is with intercooler, and then given right here we have a regenerator and reheater. Okay, the pressure ratio across stage of compressors and turbines is 3. The air enters each stage of the compressor is 30. Okay, the pressure ratio across each stage of compressor and turbine is 3. What is that? The 3.
3 over 1, sir.
Yeah?
3 over 1.
Yeah, of course lah. 3 over 1. 3 over 1 is 3 lah. Good. What is the meaning of this? The pressure ratio across each stage of the compressor and turbine. What can we write there?
Completely intercoolant.
Pardon?
Same temperature.
This meaning that each compressor and each turbine have the same pressure ratio. What is the pressure ratio of the compressor number 1? P2 over P1. What is the pressure ratio of stage 2 compressor? P4 over P3. Okay? What is the pressure ratio of the first turbine? P6 over P7. And what is the pressure ratio of the second turbine? P8 over P9. Okay? So these 3 refers to the pressure ratio of this one. Maximum divided by minimum, P2 over P1. Same as pressure ratio of the compressor, P4 over P3. For turbine side, maximum is 6 over 7. And for the second turbine is P8 over P9. And this is all S3. Okay? That is the meaning of this. The pressure ratio across each stage. So this each stage equal to 3. And the air enters each stage of compressor. This is each stage of compressor. And referring to the air enters. So this is air enters at the first stage. This is air enters at the second stage. The temperature is 30. Okay, it's 30. Meaning, what could we write the 30 as for? The air enters each stage of the compressor. The air enters each stage. This is the air enters first stage. Air enters second stage. So what can we write of the 30 degree?
Complete intercoolant.
Okay, it's a complete intercooling. In terms of equation, what can we write?
T1 equal to T3.
T1 equal to T3. T1 equal to T3, which is equal to 30 degrees C. Okay. The air enters each stage of the compressor. The air enters each stage of the turbine 950. Okay, the air enters each stage of the turbine 950. So this is entering 950. This is also entering 950. So what we can write here is the T6 is equal to T8. T6 is equal to T8 equal to 950. Okay? So that is the data given. The data given. So let us look, what are we going to solve for? Okay. So this is the first set of questions. Part A. Assuming no regenerator is used, meaning what? What could we get from this statement? Anyone?
The thermal efficiency is lower. So
Yeah, I know. Yes. It should be lower lah. But as far as what we are going to look into this schematic diagram, assuming no regenerator, where is the regenerator? This is our regenerator, correct? If there is no regenerator, what happened to T4 and T5?
remain same.
Yes, meaning that the T4 is equal to T5. And also there is no T10. Okay, there's no T10. So state 10 tak ada. Okay, so right now we are going to sketch the TS diagram. Okay, we are going to sketch the TS diagram for this case, for the first case. So how many pressure involved? How many pressure involved? What do you think?
3.
3 pressure. Anyone else have the agreement of 3 pressures? Okay, we are going to sketch 3 pressures. Because of this pressure ratio across each component, they are the same, meaning that we are going to have the same line as the intermediate pressure. Okay, one line, because the same pressure ratio. Okay, same pressure ratio, meaning that this is in the middle. And what is the overall pressure ratio? The overall pressure ratio in this case should be 9. 3 times 3. That is our overall pressure ratio. Okay. So let us sketch the compression process. Intercooler. Second compression. Second, the first expansion. And then we are having the same temperature entering each turbine, meaning that these are the same level. Okay. So let us transfer the numbering given in the schematic diagram to this TS diagram, which is no regenerator is used. So this is 1, 2, 3, 4. And the number 4 is equal to, sorry, number 4 is equal to number 5. Okay, T4 is equal to 5. And then first combustion chamber, 5 to 6. 6 to 7 before the reheater. After the reheater, 8. And then we have, after the expansion in the second turbine, this is 9. So it stopped right there. There's no point 10. Okay, there's no point 10 in this case. So this should be our TS diagram look like. Determine the work, okay, determine the net work produced in kilojoule. You know that when we involving the W net, then we have to get what is the summation of work, because this is as one shaft. Okay, one shaft. So this is number 1. Number 2, we are going to use this formula. W net equal to W6 7 for the first turbine plus W89 for the second turbine minus W12 for the first compressor minus W34. Okay. What do you think of the work 6-7 and work 8-9? This is CPG T6 minus T7. This is CPG T8 minus T9. This is CPA T2 minus T1. This is CPA T3 minus T4. But in this case, we are assuming everything as air. Okay, you're not mistaken, everything is as air. Oh no, we need to get also for the gas. Okay, different. So we need the temperature of 1, 2, 3, 4. 4 equal to 5, 6, 7, 8, and 9. So, meaning that after this, what we have to do? We have to get all the temperature. Okay, get all the temperatures. Okay. So, what is T1? T1 is given as 30. Okay. And the next temperature, I think, will continue next lecture on Wednesday, inshallah. Okay, we try to solve this problem on Wednesday. So before we leave, I will take your attendance. Any question, guys?
So, okay, sir.
All right. If there is your attendance, please send in. Okay, Amirul, betul tu Amirul, P1 over P2 equal to P3 over P4 equal to P6 over P7 equal to P8 over P9, which is equal to 3.